Suppose if the single line to ground fault happens with a fault impedance, ZF. That means yesterday we have discussed a dead short circuit fault. Suppose if the single line to ground fault happens with a fault impedance of ZF, then what would be the change in the fault current? That we will discuss now. Let us not go into the derivation part, just I'll give you the result. So this is Zn, this is Zg1. Okay, this is EA1, EB1, EC1. Okay. Now, if the short circuit happens through some fault impedance, say ZF. So ZF is the impedance between the faulted conductor and the ground. Now you see how the fault current will flow. The fault current will start from the source. It will go through this conductor. It will go to the faulted impedance and then to ground, and it will enter through the neutral. So any current should have a closed path, then only it will flow. So this is the direction of the fault current. Understand? Now, so now I can imagine that the impedance of fault and neutral grounding impedance both are in series, isn't it? See, same fault current, the same IF fault current will flow through the ZF as well as the neutral of the alternator. So I can treat my ZF and Zn as if they are in series. So my Z0, which I have defined yesterday I have defined Z0, that is equals to Zg0, zero sequence impedance of alternator plus 3 Zn. It was Z0 for dead short circuit. Understand? Here the only change is for short circuit with faulted impedance, ZF, then your Z0 value become, simply you have to add, instead of Zn you have to write Zn plus ZF, Zg0 plus 3 into Zn plus ZF. Understand? Okay, because we are, as both ZF and Zn are in series, we can directly add them. So your total impedance that will come as Zn plus ZF. Understand? So this is the concept. So only change would be this one. Again, the per unit fault current is given by the same formula. IF per unit is equals to, what is IF per unit? You're going to get 3 divided by Zg1 plus Zg2 plus Z0 if the fault occurs at the terminals of the alternator. There is no change if the fault occurs anywhere in the system. So this simple thing we have to remember, if the fault, LG fault, occurs with a faulted impedance of ZF. Instead of Zn, you have to write Zn plus ZF. So your Z0 value only will change. Understand? Now we'll discuss the line-to-line fault. Again, let us consider, first we will consider a no-loaded alternator at the terminals of which a line-to-line fault occurred. Then we will extend the same idea to the line-to-line fault at any point in the power system network. Okay. So again, let us consider a no-loaded alternator. Let us consider a no-loaded alternator at the terminals of which a line-to-line fault occurred. Let us consider a no-loaded alternator at the terminals of which line-to-line fault occurred. So now, again, my system would become EA, EB, EC. So this current is IA, that is equals to 0. We are assuming line-to-line fault occurred between the conductors, B phase conductor and this one. So this is IB, this is IC. Understand? Now, the fault current is this one because of the line-to-line fault, IF. The voltage at this point is VB. The voltage at this point is VC. Understand? Okay. Now, what are the boundary conditions which we know before? What are the how the fault current will flow? I will tell you first. The fault current will flow in this fashion. It will start from, say, B phase source. It will go like this, and it will. So this is the path in which the fault current will flow. The direction I am writing it as this one. So this is the direction in which the line-to-line fault current will flow. Understand? So directly you can tell that there is no ground or neutral that is involved in LL fault. So there are no zero sequence currents. There are no zero sequence currents. Okay, directly you can say for zero sequence currents will only flow through the ground and neutral. Since my LL fault current is not flowing through any ground or neutral, so in LL fault there will not be any zero sequence currents. We'll prove it. So now the boundary conditions for this would become, the boundary conditions or initial conditions which we know beforehand are IA is equals to 0 because before fault the alternator is under no load. IA is equals to 0. Fault current is equals to IB. Fault current equal to IB, and the same thing you can write it as fault current is in opposite direction of IC, so I can write it as IC is equals to minus IF. IC is equals to minus IF, or I can write IB is equals to IB plus IC equals to 0, which implies IC equals to minus IB. That is one more result. Next, here, what is the voltage of VB and voltage of VC? Since it is a short circuit between these two voltages, voltage VB is equals to voltage VC. Voltage VB equal to voltage VC. So these are the boundary conditions which we know before doing the analysis. One is IA equal to 0. The other one is IB plus IC equals to 0 and IC equals to minus IB. The third one is VB equal to VC. Okay. Again, if we calculate the sequence currents, sequence currents, what you are going to get? IA0, IA1, IA2 is equals to 1 by 3 into 1, 1, 1, 1, 1, alpha square alpha into the IA value is what? We have to write IA, original unbalanced current, IA, IB and IC. Okay, but we know what is IA. IA value is 0. IA value is 0. And we also know IC value is equals to minus IB. IC value equals to minus IB. So if I substitute this condition, what I'm going to get? So my IA naught value will become, you see, 1 by 3 into 0 IB minus IB, it will become 0. And your IA1 becomes alpha minus alpha square into IB, and your IA2 becomes alpha square minus alpha into IB. Sorry, alpha minus alpha square into IB. The second thing will become alpha square minus alpha into IB. Yeah, sure. So what is the conclusion you can draw from this one? The zero sequence currents are absent in the LL fault. First conclusion which you have to remember is,
Sir, 1 by 3, sir.
yes ma'am, 1 by 3, I'm sorry, 1 by 3.
IA1 alpha plus alpha square into IB.
No, why plus ma'am? See, 1 into 0, alpha into IB, alpha square into minus is there.
Okay, sir.
Okay. Okay.
Okay.
So first result which we have to remember is there are no zero sequence. Someone mute. There are no zero sequence currents in LL fault. There are no zero sequence currents in LL fault. That is, zero sequence currents are 0. Then the second point is, when there are, that is, your IA naught, IB naught, IC naught value is equals to 0. Okay. So in this case, your neutral voltage formula is 3 IA naught into Zn. Mod Vn is equals to 3 IA naught into Zn. This value is 0. This value is 0. That means neutral voltage is same as ground voltage. Same, both are 0. Neutral grounding does not affect LL fault. That means whether you ground neutral, whether you leave it open, whether you short circuit it, whether you ground through resistor inductor, the LL fault is not going to get affected. Neutral grounding does not affect LL fault. Very common type of questions which they ask on these things. The first point is the zero sequence currents are not present in LL fault, they are 0. The second point is the neutral voltage for LL fault is 0. So neutral voltage and ground voltage are same. So neutral grounding impedance does not affect the LL fault. Three important results. The next point is your magnitude of IA1. Leave about this one. If you simulate the fault in conductor A and conductor C, then you will get some other result. But however, the general result is mod IA1 is equals to mod IA2. Okay, the positive sequence current magnitude is equal to negative sequence current magnitude. Okay, magnitude wise. Next, what is fault current? IF is equals to IB. IF is equals to IB, which we have seen from the previous slide. So our fault current is equals to IB. Understand? Now, from this relationship, how I can write this one? If I take this relationship, how I can write my IB will become, sorry, my IF will become 3 times IA1 divided by alpha minus alpha square. So I'm cross multiplying this with 3 times. So it becomes 3 IA1 divided by alpha minus alpha square. That is my fault current. So if you take the magnitude of fault current in calculator, if you calculate the magnitude of alpha minus alpha square, it is going to get root 3. So 3 divided by root 3, you are going to get root 3 into IA1. Root 3 into IA1. Understand? So your fault current equals to root 3 into IA1. Since IA1 magnitude is equals to IB1 magnitude. So the second thing important is your magnitude of fault current is equals to root 3 times magnitude of positive sequence current, or root 3 times magnitude of negative sequence current. This is your fault current in LL fault. In LL fault. Okay. The next important conclusion is the third boundary condition which we had was VB is equals to VC. VB is equals to VC. So how you can write VB value? So how you can write VB value? Since now the system is under unbalanced condition, these voltages are unbalanced. So every unbalanced voltage or every unbalanced term we are writing as the sum of its sequence components. So it will become VB naught plus VB1 plus VB2, that is equals to VC naught plus VC1 plus VC2. Understand? So VB naught, VC naught same, because VA naught, VB naught, VC naught both are same. Now how I can write VB1? VB1 is equals to alpha square into VA1. VB2 is equals to alpha into VA2. That is equals to VC1 is alpha into VA1 plus alpha square into VA2. If you write in terms of the VA1, VA2, this will be the values. So if you bring down this one, alpha square minus alpha into VA1 will be equal to alpha square minus alpha into V8. So both cancel. So one more conclusion in LL fault, the two sequence voltages are same. The two sequence voltages are same. Understand? So how I can write VA1 from the sequence network of alternator? VA1 I can write it as EA1 minus IA1 ZG1, that is equals to VA2 I can write it as minus IA2 into ZG2. Minus IA2 into ZG2. Okay. Now the same thing I can write it as, which implies EA1 is equals to IA1 ZG1 minus of IA2 ZG2. So now we already know that minus IA2 is equals to, from these two relationships you can write IA1 is equals to minus IA2. From these two you can write IA1 is equals to minus IA2. So which implies you're going to get EA1 is equals to IA1 into ZG1 plus ZG2. Since I'm writing minus IA2 is equals to IA1. So IA1 value will become how much? EA1 divided by ZG1 plus ZG2. So this is your IA1. This is your IA1. Okay. Now what is my fault current? My fault current is root 3 into IA1, that is equals to root 3 into EA1 divided by ZG1 plus ZG2. So this is the fault current formula for LL fault. LL fault. Fault current formula for LL fault. Okay. If the values are given in per unit system, fault current IF per unit will become simply root 3 into 1 at an angle 0 divided by ZG1 per unit plus ZG2 per unit. Okay, that is the per unit fault current. Okay, we don't require any zero sequence impedance to calculate the LL fault current. We only require positive and negative sequence impedance of the alternator. Okay, so next point is, for an LL fault at any point in the power system network, suppose the fault occurred at any point apart from the generator terminals, for an LL fault at any point in the power system network, then IF per unit value will become, IF per unit is equals to root 3 divided by Z1 equivalent per unit plus Z2 equivalent per unit. So where Z1 equivalent is the Thevenin's positive sequence Thevenin's per unit impedance between fault point and reference. Z2 equivalent is the negative sequence Thevenin's per unit impedance between fault point and reference, which we already know how to compute for the various fault locations. Okay, that is the per unit fault current. Okay, next, I actual means same formula. IF actual means IF per unit into I base. IF per unit into I base. Depending upon the location of the fault, you have to choose the base current. The next short circuit MVA is equals to, again same formula, base MVA into IF per unit. Understand? So that is about the LL fault. For LL fault, what you have to remember is that you only require the positive and negative sequence impedance. Neutral grounding impedance or zero sequence impedance does not come into picture. Okay. So if the fault occurs at the terminals of generator, you have to use this formula. That is root 3 divided by ZG1 plus ZG2. If LL fault occurs at any point in the power system, you have to use this formula. Understand? Now, next, so my point is, just roughly I'm drawing. So here we thought that if the fault between the two lines occurs with a fault impedance ZF, that is the case. Okay, if the fault occurs between the two lines with a faulted impedance of ZF, then your fault current will become, IF per unit will become, it is again root 3 divided by root 3 into EA1 divided by, previously we had Z1 G1 plus ZG2. Now you have to add ZF in series with this. So this is the fault current when you have a ZF faulted impedance. Okay, in per unit system it will become, IF per unit will become root 3 divided by ZG1 per unit plus ZG2 per unit plus ZF per unit. So if there is a faulted impedance, then you have to incorporate in series with the positive and negative sequence impedance in this one. That is one more important point. If the fault occurs through a fault impedance, then this is the condition. Okay. The last point in LL fault is simulation diagram. That means how the positive and negative sequence networks are connected in case of the LL fault. The first point you have to remember, you only require positive and negative sequence networks. You don't require zero sequence network to simulate the LL fault. Okay. What are the conditions we know? IA1 is equals to minus IA2. That is one condition. VA1 is equals to VA2. These are the two conditions that have come across when we analyzed the LL fault. So both conditions must be satisfied. You have to draw the sequence network satisfying both the conditions. So it will become so this is EA1, ZG1, this is IA1, so this value is VA1. So this should be equal to this one. So how it would become? So this is ZG2, this is say IA2, and this value is VA2. Okay, now you can see at this point, if you apply nodal analysis, what you're going to get? Both sum of entering currents, if you write IA1 plus IA2 is becoming 0, which is satisfying the condition. This point voltage is VA2 same as VA1. So VA1 is equals to VA2 and IA1 plus IA2 is equals to 0. So both are connected in anti-parallel. Both are connected in anti-parallel. So this is how you simulate the LL fault. Understand? Next we'll go to the last asymmetrical fault, that is line to line to ground fault. Line to line to ground fault. Again, let us consider a no loaded alternator. Again, let us consider a no loaded alternator at the terminals of which a LLG fault occurred. Understand? So let us assume the fault is occurring involving phase B and phase C and ground. So this is IA is equals to 0. Why? Because before fault system is under no load. This is EA1, sorry, EA, EB, AC. This is ZG1, ZG1 and ZG1. Okay. Now, this is ZN, neutral grounding impedance, ZN. Now let us see how the fault current will flow in the system. The fault current will flow this is one path in which the fault current will flow. This is the other path in which the fault current will flow. Both currents gets additive here. So okay. So the red marks indicates the fault current direction. Once this fault goes through the ground, again it will enter through the system neutral and again it gets divided. Okay. So this is how the fault current will flow. Fault current will flow. Understand? Now, here the current is flowing through neutral and ground, so that means the zero sequence components are present. So what boundary conditions which we know beforehand? See here, the voltage of ground is 0. So what is the voltage of conductor B is 0. The voltage of conductor C is 0. Okay. Now boundary conditions which we know. Boundary conditions or initial conditions which we know beforehand are IA is equals to 0, VB is equals to VC equal to 0. My fault current IF will become, you see, here it is the current is IB, here the current is IC. So the total fault current IF will become sum of IB plus IC. Sum of IB plus IC. This is the total fault current. Okay, so these are the boundary conditions which we know before the analysis. Understand? Now, you can directly tell any fault current that is flowing through the ground, any fault current that is flowing through the ground, you can directly write IF is equals to 3 IA naught. So your fault current is 3 times IA naught. That you can directly tell. Okay. And here the neutral voltage also will become 3 times IA naught. 3 times IA naught into ZM. This is your neutral voltage. These results you can directly tell by looking at the fault. But however, we will prove them. Understand? Now, here we calculate the sequence voltages. We calculate sequence voltages. So, VA naught, VA1, VA2, that is equals to 1 by 3 into 1 alpha square, 1 alpha square alpha into the original unbalanced voltages are VA, the VB is 0, VC is also 0. So from this what you are going to get, VA naught is equals to, VA1 is equals to, VA2 is equals to 1 by 3 into VA, 1 by 3 into, here the first result that we will get in the LLG fault is that all three sequence voltages at the fault point is same. That is VA naught equal to VA1 equal to VA2. Okay. So if we'll continue our discussion here, VA naught is equals to VA1 is equals to VA2, that is VA divided by 3, and second result is IA, that is equals to IA naught plus IA1 plus IA naught, that is equals to 0. So what is the result here which you have to remember? In LLG fault, in line to line to ground
IA1
fault.
plus IA2, sir.
Yes, IA1 plus IA2. I'm sorry. Yes, IA1 plus IA2. Okay. So in LLG fault, the sum of all three sequence currents, is 0. In LLG fault, the sum of all three sequence currents is 0. And second result is, in LLG fault, all three sequence voltages are same. So this is exactly opposite to LG fault. If you can observe, in LG fault, all three sequence currents are same and sum of all three sequence voltages is 0. Okay, so you can write this one is LLG fault. You should not write exactly opposite. There is one word called is dual of LG fault. Whatever results there you get, exactly opposite results you will get in the LLG fault. Dual means, I am telling you few examples. What is the dual of series? Parallel. What is the dual of inductor? Capacitor. What is the dual of open circuit? Short circuit. What is the dual of current? Voltage. Understand? So likewise, LLG fault is the dual of LG fault. There in LG fault, the sum of all three sequence voltages is 0. Here, the sum of all three sequence currents is 0. There in LG fault, all three sequence currents are same. Here in LLG fault, all three sequence voltages are same. So that you have to remember, that is a subtle difference here. Okay. So LLG fault is the dual of LG fault. Okay. Now, continuing our discussion. My fault current is given by IB plus IC. If you can go back and look at the figure in the previous slide, my fault current is, the total fault current is IB plus IC. So let me see what is that my fault current that I am getting. So now, since the power system is unbalanced, every component I have to write as sum of sequence components. So it will become IB naught plus IB1 plus IB2 plus IC naught plus IC1 plus IC2. Okay. So this I can write it as IB naught and IC naught are same. So I'm writing this as 2 times IA naught, because we always take reference components in terms of A. So 2 IA naught plus IB1, I can write it as alpha square into IA1, IB2 as alpha into IA2 plus IC1 as alpha into IA1 plus alpha square into IA2. Okay. So this will become 2 into IA naught, 2 into IA naught plus, if I take alpha square plus alpha common in all this, then I'm going to get IA1 plus IA2. IA1 plus IA2. Understand? So here I know two results. What are the two results that I earlier know? I know that alpha square plus alpha plus 1 is equals to 0. So which implies alpha square plus alpha is equals to minus 1. That is the first result which I know. The second result which I have already seen here is the sum of IA naught plus IA1 plus IA2 is 0 for LLG fault. So IA1 plus IA2 will become how much? IA1 plus IA2 will become IA1 plus IA2 will become minus IA naught. It will become minus IA naught. Understand? So if I substitute those values here, what I am going to get? What I am going to get? 2 IA naught plus alpha square plus alpha is minus 1 multiplied by minus IA naught. So this will total will give rise to 3 IA naught. So my fault current in LLG fault is 3 times IA naught. 3 times IA naught. Okay. So for any fault that involves ground, if the fault current flows through the ground directly, you can write your fault current as 3 IA naught. Okay. That is the next important point. Now, so from this discussion, we know that from the previous slide, we know that VA naught, VA1, VA2 are same. So if I expand this one, VA naught is equals to VA1 is equals to VA2. Sorry. So what is VA naught? From sequence networks, I can write VA naught is equals to minus IA naught Z naught, that is equals to VA1 is equals to EA1 minus IA1 ZG1. VA2 is equals to minus IA2 into ZG2. Okay, ZG2. We also know Z0 is equals to ZG0 plus 3ZN. If it is a dead short circuit, Z0 is equals to ZG0 plus 3 into Zn plus Zf if the fault occurs through an impedance. So this is standard. This will not change for any fault. Okay. Now from this, I can write, from these relationships, I can write, if I compare 1 and 2, I am going to get IA naught is equals to minus of EA1 minus IA1 ZG1 divided by Z0. This is the first relationship. If I compare this term and this term, okay. If I compare the first and the second and the third term, that means if I compare this term and this term, I'm going to get what? IA2 is equals to minus of IA2 is equals to minus of EA1 minus IA1 ZG1 divided by ZG2. Okay, so I'm going to get IA0 as this one, IA2 as this one. Substituting these two results in IA0 plus IA1 plus IA2 is equals to 0 and simplifying. I'm substituting above two results in this equation which we already know for LLG fault, and simplifying we are directly going to get, I'm directly writing the answer. IA1 will become EA1 divided by ZG1 plus parallel combination of ZG2 and Z0. You only have to remember this result. So your IA1 is equals to EA1 divided by ZG1 plus parallel combination of ZG2 and Z0. Understand? That is the first thing you have to remember. The second is simulation of LLG fault. Simulation of LLG fault. So here what two results that must be satisfied? The first result is VA0 is equals to VA1 is equals to VA2. This is one condition. And the second condition is IA0 plus IA1 plus IA2 is equals to 0. So we have to draw the simulation network such that both conditions are satisfied. So it is very, so voltages are same means it should be parallel circuit. The summation of all three currents must be 0. So the circuit would become this is first one EA1 ZG1 IA1. The second one would be ZG2. The third one would be Z0. Okay. So here the current direction you have to reverse. This is IA2. This is IA0. So if you see the voltages, it will become, this is VA1, this voltage is VA2, this voltage is VA0. So all three voltages are same, and if you apply KCL here, what you are going to get? Here you got VA1 is equals to VA2 is equals to VA0. And if you apply KCL at this point P, let us say IA1, sum of entering current equals to sum of all three entering currents is 0. IA1 plus IA2 plus IA0 is equals to 0. So this is the simulation diagram of the LLG fault. Understand? So there you can observe in LG fault all the sequence networks are connected in series. In LLG fault all the sequence networks are connected in parallel. Again dual. Understand? Now I want my fault current. So fault current magnitude only if I want, that is 3 into IA naught. 3 into IA naught. So from this one, how to calculate IA naught? Only if I want magnitude, I am not worried about direction. So the total current, if you take these two branches, if I take these two branches alone, and suppose this is a current IA1 that is entering into these two branches. So I want my IA naught value. I want my IA naught value. So if you apply current division rule, my IA naught will become the total current entering these two parallel branches multiplied by opposite impedance divided by the total impedances. So from this current division rule, you can write mod IA naught is equals to total current that is entering is IA1 into what is the opposite impedance? Opposite branch impedance is ZG2 divided by the total impedance is ZG2 plus Z0. So this is how you calculate the magnitude of IA0. So your fault current will become, IF will become, that is 3 times IA0. Only magnitudes we are calculating. This will become 3 times IA1 into ZG2 divided by ZG2 plus Z0. ZG2 plus Z0. Understand? Okay. So for calculating the fault current, you have to remember two formulas here. This is one formula which you have to remember where you are approaching the fault current. So in the fault current, you have one more term IA1. To calculate IA1, you have one more formula which we have already computed in the previous slide. That is this one. So if you remember both the formulae, then you will be able to calculate fault current for the LLG fault. Okay. So again, I am writing the formulae. Two formulas is which you have to remember. IA1 positive sequence current is given by EA1 divided by ZG1 plus parallel combination of ZG2 and Z0. Okay, that is one formula. So in per unit system, this will become, in per unit it will become, I'm just simply writing in per unit 1 divided by ZG1 plus parallel combination of ZG2 and Z0. In per unit, this is the value. So after finding out this IA1, your IF will become 3 times IA1 into ZG2 divided by ZG2 plus Z0. This is the fault current. This is the fault current in case of LLG fault. 3 times IA1 multiplied by ZG2 divided by ZG2 plus Z0. Okay. Remaining all formulas are same. Voltage of neutral is equals to IF into Zn. IF into Zn. Voltage of neutral is equals to IF into Zn, or you can write 3 IA0 into Zn, whichever you know, according to that you can calculate. Formula for fault current, again short circuit MVA formula is also same, base MVA into IF per unit. Most of the time they will not ask you to compute the fault current in LLG fault because it is little bit lethargic. They only ask the other things about LLG fault. Okay. Now, next important point is if the neutral is not grounded in LLG fault. If the neutral is not grounded in LLG fault, that means if there is no neutral grounding, this path is not there, then your LL, this figure we have seen already in the LL fault. So if the neutral is not grounded, your LLG fault becomes LL fault. Very, very simple result. Where if you remove the neutral grounding, your LLG fault becomes LL fault. Okay. So this point you remember. If neutral of alternator is not grounded, If the neutral of alternator is not grounded, then LLG fault becomes LL fault becomes LL fault. Understand? So this is about the line to line to ground fault. Determine the magnitudes of symmetrical components. We are using IA1, IA2, IA0. We are using international standard. The question they asked in IR1, IR2, IR0. So don't get confused. Okay, we use ABC as our three phases. Some questions may come by using RYB as phases. So don't confuse. You first write those terms in this one. Your life will be easy. So he's asking, determine the magnitudes of IA1, IA2 and IA0 of the currents for a three-phase, three-wire system where the short circuit occurred between R phase and Y phase. The fault current is 100 ampere. This question they asked for 5 marks, you know. Very simple question. Without putting pen on paper, you can tell the answer if you know the concept. So what he's telling, in a three-phase, three-wire system, between R phase conductor and Y phase conductor, in our language between phase A and phase B, a short circuit occurred. This fault current magnitude is 100 ampere. Now he's asking, what is the magnitude of IA0? What is the magnitude of IA1? What is the magnitude of IA2? Anyone? What is the fault?
Line to line fault.
It is a line to line fault. So what is the formula for line to line fault current? IF is equals to √3 into IA1 or √3 into IA2. The fault current magnitude is √3 times the positive sequence current magnitude or negative sequence current magnitude. So from this we can directly get IA1 is equals to 100 by √3 ampere. IA2 is also 100 by √3 ampere. Any doubt? Okay. Now in LL fault, are the zero sequence currents present?
No, 0.
So this is 0. This is 0, that's it. Isn't it? In an LL fault, the fault current magnitude is √3 times the positive sequence current and √3 times the negative sequence current magnitude. So from that I can directly tell my IA1 will cause fault current divided by √3, that is 100 by √3. IA2 is equals to 100 by √3. Same magnitude. Okay, and IA0 value is 0. If you go to prove this one, it will take 4 to 5 pages. Understand? But if you remember the concept, the question will be very easy. Next, read the second question.
The positive sequence component of the voltage at the point of fault in the power system is 0 for a...
Which fault? The positive sequence voltage, what he is telling, VA1 is equals to 0, that is equals to EA1 minus IA1 Z1, ZG1. This is equals to 0 for which fault? What should be the fault? He is asking. Okay, EA1 minus IA1 ZG1 is 0 for symmetrical faults. For symmetrical fault, that is triple L fault and triple LG fault, the positive sequence voltage is 0 at the fault point. For no other fault, the positive sequence voltage is 0, except for the symmetrical faults. You can check our analysis. That's why I always encourage you to go through the lecture and write notes. Lectures may be very beautiful to watch, very convenient, but unless you have your notes, it is very difficult to follow. You can go back and easily refer. Understand? So for symmetrical faults, at fault point, your positive sequence voltages are 0. Okay. Symmetrical faults means the fault will affect all three phases equally. Next, this is GATE 2019 question. Read this question. Try to at least give it a try. What he's asking you, try to get the feel. So here, what he's telling, there is one generator. Synchronous machine generator whose the positive sequence voltage is Z1. The positive sequence voltage is Z1. Negative sequence voltage is Z2. Zero sequence voltage of the generator is Z0. Okay. If the line-to-line fault occurs with a fault impedance ZF, the fault current is IF1. So IF1 is the fault current for, give me a minute. So IF1 is the fault current for LL fault with ZF as the fault impedance. That means he's telling the line-to-line fault is occurring with a fault impedance of ZF. Okay, so excuse me for that. I have one very young small son. He doesn't listen to anyone. So yes, IF1 is the fault current for LL fault with ZF. So what is the formula for the fault current with fault impedance ZF? So IF1 will become EA1 divided by our formula which we have learned is ZG1 plus ZG2 plus ZF with fault impedance. So here instead of ZG1, ZG2, what terminology he gave? He gave Z1 and Z2 are the positive and negative sequence impedance of the alternator. So it will become Z1, Z2. Okay. Now what he's telling, this IF1 is equals to K into IF, where IF is the fault current for the same line-to-line fault with zero fault impedance. That means if the line-to-line fault occurs like this without any fault, then my fault current is IF. So what is the formula for IF? The fault current without any fault impedance, it will become EA1 divided by ZG1 plus ZG2 according to our formula. Here ZG1, ZG2 values are Z1 plus Z2. Okay. So this is the formula for IF. This is the formula for IF1. But what he is telling, IF1 is equals to K into IF. So in place of IF, if I substitute this one, EA1 divided by Z1 plus Z2, then what relationship you are going to get? That means he wants you to calculate ZF in terms of this one. Okay. So since these two terms are equal, both these two terms are equal, EA1 gets cancelled, EA1 gets cancelled, and if you cross multiply, you are going to get Z1 plus Z2 is equals to K into, see how I am writing, Z1 plus Z2 into K plus K into ZF, So if I arrange these terms, what I am going to get? If I arrange this term, what I am going to get? K into ZF will become, if I send this terms to this side, Z1 plus Z2 into 1 minus K you are going to get. So your ZF will become 1 minus K into Z1 plus Z2 divided by K. That is your option. Which is the right option? A is the right option. Okay, he's simply testing whether you know the difference in fault currents when the fault is a dead short circuit line to line fault and a normal short circuit with a fault impedance of ZF. A two bus system is given, single line diagram is given, and its zero sequence network is also given. So he only gave the single line diagram and its zero sequence network. But he wants you to tell what is the transformer T1 connection and what is transformer T2 connection.
B is
Super, very good. B is the right answer. Okay. See, the first transformer, just look at this one. Series switch is closed. Series switch is directly closed without any impedance. So the primary side of the first transformer should be star connected and solidly grounded. Star connected and solidly grounded. Okay, because the series switch of the first transformer is closed directly without any impedance. So it must be star connected and solidly grounded. Okay. The secondary side, neither shunt switch is closed nor series switch is closed. So shunt switch is not closed means it is not delta. Series switch also not closed means it is star connected without any grounding. It is star connected without any grounding. So the first transformer it is primary side is star solidly grounded, secondary side is star ungrounded. Okay, now let us come to the second transformer. Again in second transformer, after the transmission line reactance, there is a direct connection. That means the series switch is directly closed. The series switch is directly closed means it should be star connected and solidly grounded. In the secondary side, the shunt switch is closed, the series switch is open. Shunt switch is closed and series switch is open. So it must be delta. It must be delta. So which is the right option? B is the right option. B is the right option. Understood? Yes or no? So if you learn this question, exactly the method in which we learned, exactly in the same way he has drawn the zero sequence network. Okay. Now look at this question and try to answer. A 50 MVA 11 kV three-phase generator, when it is subjected to three-phase fault, the fault current is J5 per unit. The fault current is J5 per unit. Okay, so three-phase per unit fault current for a generator, it is given by 1 at an angle 0 divided by ZG1. This value how much is telling? 5 per unit. 5 per unit. Understand? Now, when the same generator is subjected to line fault, then positive sequence current is J4 per unit. Positive sequence current is minus J4 per unit. Don't worry about the symbol, only take the magnitude. Okay, so it is not IF per unit, he is telling. IA1, positive sequence current magnitude, that is given by, what is the formula? 1 at an angle 0 divided by ZG1 plus ZG2. Which fault this is? LL fault. He did not tell the total fault current. He said the positive sequence current is J4. So this value is 4 per unit. 4 per unit. Now he is asking what is the positive and negative sequence reactance of the generator? What is the positive and negative sequence reactance of the generator? So directly, when a three-phase fault occurs, the fault current is 5 per unit. We are only taking the magnitude. So which implies 1 divided by Zg1 is equals to 5, which implies Zg1 magnitude is 1 divided by 5. You're going to get 0.2 per unit. 0.2 per unit. Since the value is all reactances, so he has mentioned the positive sequence reactance will be J 0.2 per unit. Now again coming back to here, so if you consider the magnitudes only, 1 divided by Zg1 value is 0.2 plus Zg2 magnitude is equals to 4. So which implies 1 by 4 is equals to 0.2 plus Zg2. So 0.25 is equals to 0.2 plus Zg2. So your Zg2 value will become 0.05 per unit. That is J you have to include. So this magnitude we have calculated as 0.05. So if you want the exact inductance, it will be J 0.05. Which is the right option? Option A is the right option. Okay, very simple question. If a three-phase fault occurs, the fault current is J5 per unit. Okay. If a line-to-line fault occurs, the positive sequence current is minus. Actually, here also you should give minus J per unit only, minus J5 per unit only, because all the fault currents are inductive currents only. Minus J symbol tells they are inductive currents. Okay. There is a mistake in question, that is the fault current in case of three-phase fault is minus J5 per unit. The positive sequence fault current in case of line-to-line fault is minus J4 per unit. Then what is the positive sequence and negative sequence reactance of the generator? That is the question. So by using their formula, we have computed this one, and then by using this value, we have computed the value of Zg2. Okay. Now look at this. The connection diagram of sequence networks for a particular fault on a power system is shown in the figure. The type of fault is. He gave the simulation diagram. He's asking what is the fault. Tell me. Look carefully and tell what is the fault. What is the fault? See, all three sequence networks are there. So it should be the LG fault or LLG fault. In LL fault, we don't get the zero sequence network. So the choice is between LG fault and LLG fault. Now you have to check whether all the sequence networks are connected in series or parallel. Okay. If you look at this one, this point is same as this point is same as this point. This point is same as this point is same as this point. So all are connected in parallel. It is a parallel connection. Appearance is double line to ground fault. So it is a parallel connection. That only is testing. Because suppose if you assume this point as P, if you apply KCL, what are the currents that are reaching this point? You see, this current is IA0, this current is IA2, and this current it is IA1. Add all the entering currents, what you are going to get? IA1 plus IA2 plus IA0 equal to 0. Understand? Now you see this point and this point are same, this point and this point are same, this point or this point same. All the three sequence networks are connected in parallel. So it is a LLG fault, double line to ground fault. Yes, at least you should answer this one. All type of faults. In all types of faults, what sequence components are present? Positive. So A matches with the 4. Let us change the color. Yeah. So in all types of faults, there are positive sequence currents. Okay. Next. In all unsymmetrical faults, you have negative sequence currents. In all unsymmetrical faults, you have negative sequence currents. Understand? Whenever there is unbalanced, negative sequence components must come, they will come. Okay. Faults involving ground with the neutral of the system grounded. So if the neutral of the system is grounded and the fault also involves ground, then you have zero sequence currents are present. C matches with 2. C matches with 2. Faults involving ground but floating neutral. Floating neutral means ungrounded neutral. Then zero sequence currents are absent. So A is matching with 4. B is matching with 1. C is matching with 2 and D is matching with 3. So option B is the right option. Option B is the right option. Okay. So this is very, very important point. Question may come in. There are 4 questions in this list if you carefully observe. In all types of faults, what components are present? Positive sequence. Whether balanced, unbalanced, okay, involving ground, not involving ground. In any fault, positive sequence currents are there. In all unsymmetrical faults means unbalanced faults. Unbalanced faults, there are 5 types of unbalanced faults. 3 short circuit and 2 open circuit. So whenever there is unbalance, the negative sequence components are present. Understand? So faults involving ground and the neutrals must be grounded, then only zero sequence currents will flow. Okay, fault involving ground but the neutrals are not grounded, then zero sequence currents will not flow. That is the point. Understand? Very important question. Now read the first question. The zero sequence current of a generator for a line to ground fault. The zero sequence current for a generator for a line to ground fault is J 2.4 per unit. Then the current through neutral during the fault is. Come on. Is telling the zero sequence current through the generator is J 2.4 per unit. IA naught value is what is telling. IA naught value is J 2.4 per unit. Then what is the neutral current? Neutral current is 3 times IA naught. Isn't it? Neutral current is 3 times IN2. So the option will be C. The option is C. Very simple question. Understand? So if the zero sequence current of a generator for a line to ground fault, IA0 is 2.4, then what is the current through the generator neutral? Because since the zero sequence current is flowing, that means the neutral is grounded. So neutral current IA is 3 IA0, that is J 7.2 per unit. Okay. Now you see the next question. All 3 sequence voltages at the fault point and power system are equal. All 3 sequence voltages at the fault point are same. What is the nature of fault? All 3 sequence voltages means?
Double line to ground.
Very good. VA1 equals to VA2 equals to VA0. So the fault is double line to ground fault. Double line to ground fault. Understand? Okay. Now, last question. When a line to ground fault occurs, the current in the faulted phase is 100 ampere. When a line to ground fault occurs, the current in the phase in which the ground fault occurred is 100 ampere. The zero sequence current will be
Option B.
good. It is reverse of the first question. So what he is telling. So if this is my system, suppose here the fault occurred. My fault current here is 100 ampere. Okay. Now, what is the what is the zero sequence current? So same fault current will flow in LG fault. This same fault current will flow and enter into the system. So my IF in LG fault, IF is equals to 3 IA naught. So my IA naught value will become IF divided by 3, that is 100 divided by 3, that is 33.3 ampere. Okay. Now tell me this question. What is the fault?
LNG fault, sir.
Yes, very simple, LLG fault. Understand, first you see all three sequence currents are present. It should be either LG fault or LLG fault. In LG fault, all three sequence currents are same. So if all three sequence currents magnitude is values are same, then you can directly say it is LG fault. But here all three sequence currents magnitudes are different. And again, one more hint what he has given. Even if you don't give this hint also, second condition also, you can directly say it is a LLG fault. Understand?
Voltages.
Here voltages are same. So voltages are same for which fault? LLG fault. Okay. Either first condition is not given, you can tell. Either second condition is not given, you can tell the fault. Okay. Suppose had he given IA naught is equals to 2J, that is equals to IA1, that is equals to IA2, like this, you can directly say, irrespective of voltage, you can directly tell it is a LG fault. It is a LG fault. Understand?
Sir,
So, yes, ma'am.
in LNG, the sum of the sequence currents is 0. So IA negative sign.
Yeah, IA and IA2 should have negative sign. Correct. Absolutely, you are correct. But he has only given magnitudes, we should say. Okay.
Okay.
Actually, to be very exact, this and this value should have negative sign. You are absolutely right. But however, since he has only given the magnitudes, we have to consider. So then, by looking at the second condition, you can directly tell it is a LLG fault. Okay. So with this, the fault analysis is over. We have left one question that we will try to solve, and we will close today's session. Go through videos and prepare notes. Whatever important points which you want to remember, you prepare the notes. Read this question. The positive, negative and zero sequence impedance of 125 MVA, 3-phase 15.5 kV, star grounded 50 Hz generator are given. The machine is unloaded and working at rated terminal voltage. If a grounding impedance of generator is this one, the magnitude of fault current for B phase to ground fault in kiloamperes is. Very simple question. Is asking LG fault only. Okay. Is telling there is a generator. Let me not write prime mover. There is a generator which is grounded through an impedance of J 0.01 per unit. Okay. Now it is operating under no load, and at the terminals of this one, LG fault occurred. Line to ground fault occurred. Okay. The positive, negative, and zero sequence values of the impedance are ZG1 is equals to J0.1, ZG2 is equals to J0.05, ZG0 is equals to J0.01. See here, the two values are different. Understand? ZG0 is J0.01. Okay. the machine is unloaded, this one. The magnitude of fault current for a B phase to ground fault, whether it is in phase A, phase B, phase C, it doesn't matter for us. So first to calculate the per unit fault current. Per unit fault current for a single line to ground fault is given by 3 divided by ZG1 per unit plus ZG2 per unit plus Z0 per unit. Z0 per unit. Okay. So what is Z0? For calculating Z0, you have to consider two things. Whether it is a bolted fault. Bolted fault means Z short circuit. So your ZF value is 0. And whether the neutral is grounded. Yes, here neutral is grounded with some impedance. So your Z0 will become ZG0 plus 3ZN. ZG0 plus ZN because ZF value is 0. So first to calculate this one, ZG0 value is J0.01 plus 3 times this impedance is J0.03. So it is J0.04. So if I substitute this one, I'm going to get 3 divided by ZG1 value is 0.1 plus 0.05 plus 0.04. 0.04. So can someone tell me this magnitude? So magnitude of IF per unit will become 3 divided by 0.19. $15.789 per unit. 15.789 per unit. But he is asking in kiloampere, so we have to multiply with the base current. So IF actual will become IF per unit into I base. So since the base current should be calculated on the machine ratings only, 15.789 into the machine rating is 125 MVA divided by root 3 into line to line voltage is 15.5 kV. So many kiloamperes you are going to get. 15.5. 73.51, right?
Yes, sir.
73.51 kiloampere. Already he gave the in kiloampere. So this value is 73.51 kiloampere. Okay. So that's it.